Next topic is Chebyshev inequality. It's a very important inequality in majority cases. One of the last essay question in your examination. I think it's most repeated question also. You need to remember the statement also. Chebyshev inequality is let x be a random variable with mean mu and variance sigma square. Then you need to show that probability of modulus of x minus mu greater than k sigma is less than 1 by k sigma square, and p of mod x minus mu less than, here you have greater than, here less than k sigma is 1 minus 1 by k square. So you need to prove these two. So if you can prove one first inequality, the second can automatically be proved by using the complementary probabilities. So it's let us see how to prove this. You know that the formulas for variance in terms of expectations, it's given that x, its mean as mu and variance as sigma square. Expectation of x is mean, I think E of x is mu, and variance of x is nothing but sigma square. You know that formula for variance of x in terms of expectation is u of x minus e of x whole square. So to resolve the expectation, depending upon the type of variable, if it is discrete, you will initiate with sigma, otherwise you will start with integral. Let us take this as a continuous variable. Then this expectation is to be started with integral, and within the brackets you have write down the same quantity. What is e of x here? Mu into, I think this is the this is the formula for expectation. Expectation of any random variable, it starts with integral if it is continuous. You need to write whatever within the brackets, you should write the same. Here x, e of x is nothing but mu, x minus mu whole square into its PDF f of x dx. Let us take the entire real number range. As the range is not given to you, I am considering the entire range. I am going to split the entire range minus infinity to plus infinity into three different parts, as let us take in between mu minus k sigma some variable and mu plus k sigma. So I have splitted entire integral minus infinity into plus infinity into 1, 2, 3 parts. Minus infinity to mu minus k sigma, mu minus k sigma to mu plus k sigma, and mu plus k sigma to infinity. I think whenever a to b integral can be written as, if you take any intermediate value c, you can write, I think in this way you can write a to b can be written as a to c. You should start with c only, c to d, and d to b. I think you can change the limits in this way for definite integrals. So using the same one, minus infinity, I want to write here mu minus k sigma, the same function, and the second range is mu minus k sigma to mu plus k sigma. Plus mu plus k sigma to plus infinity. So I have splitted one integral into three different parts. Mu minus infinity to mu minus k sigma, mu minus k sigma to mu plus k sigma, mu plus k sigma to plus infinity. The same terms. So this integral is the sum of 3. So here the variance of x we are writing with sigma square. Sigma square, you got that as sum of 3 terms with minus infinity to mu minus k sigma, plus mu minus k sigma to mu plus, the same step I am writing again. So this sigma square is the sum of 3 terms. Okay. Now if I want to change this equals to into some inequality, this is, if you take 4 as sum of 2 plus 1 plus 1. If I want to change this, can I write that as 4 greater than 2 plus 3? So if I on RHS, we are observing LHS is equal to RHS when this is the sum of three terms. If I omit one term, I think this equal to will be turned into greater than. In the similar steps, among these three steps, three terms, if I omit the middle one, I think this equal to becomes greater than, and minus infinity to, I want to skip the middle term, so that equal to will be changed into greater than. I will write the last term again. So we have two terms here, and this equal to is being changed into unequal to. Now see girls, you have a to b f of x dx. So we call this as the lower limit, this as the upper limit. I think a less than x less than b. This is the relation between the variable here and the limits. So you have minus infinity here, mu minus k sigma here. So we can write that as minus infinity less than x less than mu minus k sigma. Similarly here, mu plus k sigma less than x less than infinity. So if you skip this infinity, we can write that as x less than mu minus k sigma, mu plus k sigma less than x. So this becomes x minus mu less than minus k sigma. So you have minus here. If you multiply both sides with minus, it becomes mu minus x. This less than becomes greater than sigma. So I think if I square on both sides, mu minus x is same as x minus mu greater than k square sigma square. By using the limits, I got x minus mu whole square is greater than k square sigma square. Similarly, here k sigma, if you shift this mu to the RHS, you will get k sigma less than x minus mu. If you square on both sides, okay, in the first inequality, you got x minus mu whole square greater than k square sigma square. In the second one, if you write this on the RHS, you will get x minus mu greater than k square sigma square. So you can write this x minus mu whole square with k square sigma square here. Here also x minus mu sigma square can be written with sigma square. Both are greater than. I think this sigma square, this sigma greater than remains the same. So we can write that as sigma square greater than, okay, the same limits, minus infinity to mu minus k sigma. We got x minus mu whole square k square greater than k square sigma square. So k square sigma square f of x dx plus mu plus k sigma infinity. Again here also k square sigma square f of x dx. So if you take out sigma k square sigma square from both the integrals as the common one, minus infinity to mu minus k sigma f of x dx plus mu plus k sigma infinity k f of x dx. I think sigma square cancels. If you bring to the RHS, you will get 1 by k square is greater than. So if you observe this one, you have minus infinity to mu minus k sigma f of x dx plus mu plus k sigma to infinity f of x dx. So while learning the basics in the random variables, we have observed that p of a less than x less than b is nothing but integral a to b f of x dx. So this integral can be written as p of, using in place of a you have minus infinity, in place of b you have mu minus k sigma, minus infinity less than x less than mu minus k sigma plus p of mu plus k sigma less than x less than infinity. So you got 1 by k square is greater than, you have p of, okay, minus infinity less than x. Let us bring this, simplify in this way. I think you have understood that step. So you got 1 by k square greater than p of minus infinity less than x minus mu less than minus k sigma plus p of k sigma less than x minus mu less than infinity. So if you observe here, you have minus k sigma and plus k sigma. I think whenever we have the values like this, we can write that as mod x less than 2. By the definition of modulus function, whenever we have minus into less than x less than 2, that is same as mod x less than 2. So in place of 2 we have k sigma, so we can write that as probability of mod. In place of x you have x minus mu, in place of 2 you have k sigma, so we can write that as is greater than probability of mod x minus mu greater than k sigma. Okay, so if you rewrite this, it becomes p of mod x minus mu greater than k sigma is less than 1 by k sigma square, which is nothing but the first inequality to prove, first part to prove. What is the second part we have? Second part you need to prove is nothing but probability of mod x minus mu less than k sigma is equal to 1 by 1 minus k square. You know that p of a bar is equal to 1 minus p of a. So you have greater than sigma here, you have less than sigma here. So p of 1 will be 1 minus probability of mod x minus mu greater than k sigma. You have less than, so using p of a bar will be 1 minus p of a bar. P of a bar will be 1 minus p of a. Probability of mod x minus k sigma will be is equal to 1 minus probability of x greater than a. So just now in the first bit we have proved 1 minus probability of mod x minus mu greater than k sigma is less than 1 minus k sigma square. So I have substituted in place of this 1 by k sigma square. So I got the second bit also. Okay, thank you.